All right, so here are our practicum problems for tonight, a couple of beam deflection problems. The first one here, I've got a 40 kip load sitting at the middle of a simply supported beam. The length, the span here is 10 feet. Cross-section of the beam is detailed out here. It's a 4-inch width and a 12-inch height, not to scale. Selected here a 2 MSI or a 2000 KSI modulus, which is roughly, it's on the high end of what we get out of southern yellow pine, which is the typical structural wood material. To find the deflection, the first thing we need is the moment of inertia. And for a rectangular cross section like this, the moment of inertia is BH cubed over 12. So we have 4 inches for B, we have 12 inches for H, since 12 is perpendicular to our neutral axis, all divided by 12. And if we calculate that out, that should come out to be 576 square inches. Sorry, not square inches, inches to the fourth. Since we have inches times inches times inches times inches, that'll be inches to the fourth. Now the deflection is the force applied times the length of the beam in inches cubed divided by 48, which is about the way it's supported, times the modulus times the moment of inertia. So if we plug in what we've got 40 kips, and I can use 40 kips as long as I use my modulus in KSI. My length is in inches, so I've got to convert the 10 feet. 10 feet's 120 inches, so that'll be what I cube over 48 times 2,000, since that's my modulus in KSI, times the moment of inertia, 576. And if we calculate that out, so we have 40 times 120 cubed divided by 48 divided by 2,000 and divided by 576. We get 1.25, and the units on that are inches. So we get 1.25 inches of deflection. Not too bad for 40,000 pounds of force on wood, but this is roughly what we'd get with two 2x12s. Two 2x12s that are so-called sistered together, where they're joined together essentially into one beam, nailed together or screwed together. So there we have 1.25 inches, 1.25 inches of deflection. Now in the second problem, we've got a cantilevered beam, and we're putting a relatively modest load out on the end there, 200 pounds or so, of a 6-foot long beam. The material that I selected for this one is 6061 T6 aluminum, and 6061 T6 aluminum has a modulus of 10 million pounds per square inch. So we're going to have to be careful about units here. Remember, we always have to make the force and the modulus consistent with each other. Before we can find the deflection, we need the moment of inertia. And since this is also a rectangular profile, we need to use BH cubed over 12. B is 3 inches. H is also 3 inches. It's 3 by 3 square. So BH cubed over 12. So we have 3 times 3 cubed over 12 gives me a modulus of 6.75, sorry, not a modulus, a moment of inertia of 6.75 inches to the fourth. So fairly modest moment of inertia. The deflection, similar equation to what we had for the simply supported beam, just a small difference. Still force times length in inches cubed, but instead of over 48 EI, it's over 3 EI. Deflections on a cantilevered beam are 16 times worse than deflections under the same conditions of the simply supported beam. So let's fill in what we've got here. We've got 200 pounds. The length is 6 feet, which in inches is 72 inches. Over 3. Now here's where we have to be really careful. 10 MSI. I put in pounds, so I've got to put my modulus in PSI. The M is for millions, that's 6 zeros. So I've got to have 10 and 6 zeros. That would be 10 million PSI times my moment of inertia, 6.75. So that's a possible area of error there, so be careful about that. You could, in principle, you could convert your pounds to millions of pounds just by dividing this by 1,000,000, but that would mean you'd have a really tiny number up in the top. I think it's easier to make a bigger number out of that 10 million, that 10 MSI. Either way, you should end up with the right value. So we'll have 200 times 72 cubed divided by 3 divided by 10 million and divided by 6.75. So there we get 0.36864 inches. So a little bit less than 3/8 of an inch deflection. 3/8 of an inch would be about 0.375, would be 0.375. So 0.36864, a little bit less than 3/8. Not bad for a 6-foot long beam and a couple hundred pounds, but it's some pretty stiff material with that 6061 T6 aluminum.